I was going to do a brand new topic, but I didn't want to go without making sure everyone understands the loop problem. Because that's one problem where if you didn't learn Newton's laws and apply them properly, you just couldn't figure it out, okay? All the other things we do, blocks sliding down planes, friction, pulleys, you have an intuitive feeling for that. But this one really is very non-intuitive, right? Here is a trolley at the top of the track. The forces on the trolley, both gravity and the force of the track, are both pushing down. And the question is, why isn't it falling down? With everything pushing down, why isn't it falling down? That's the mystery. So what's the answer you would give to somebody who says, why isn't it falling down? Yes?
It's falling down, but it's also in the left. That's why it's motion in a circle.
Yes. So they might say, well, if you say it's falling down, how come it doesn't end up here to the center of the circle? Yes? Somebody had an answer to that? Yes? Pardon me?
The forces aren't acting in the horizontal direction, so then the velocity should be changed.
No, there are no forces in the horizontal direction. The forces are all, yes?
The horizontal velocity makes the downward velocity negligible?
It's not negligible. There is an acceleration that's producing a change in velocity. But when we say an apple has a downward acceleration, you let it go and it falls down. That's what we think is downward acceleration. Here is something which is a downward acceleration, but it's not falling down. Yes?
Force changes the direction of velocity vectors over time. Acceleration times time.
Yeah.
It just changes the direction of the velocity vector.
Okay. Yes, I'll take one more answer. Yes?
I think the downward component and the horizontal component of the velocities are independent of each other. So at the same time that the cart can be falling down, it can be moving so much in one direction that it makes
Okay.
it go.
All right. So let me summarize all the different answers. First of all, one thing you should remember, there are no horizontal forces here. The forces are what I've drawn. That's why you should be very, very careful. Just because something has a tendency to move to the left doesn't mean there's a force to the left. That's the whole point of Newton's law. Force is connected to acceleration, not to velocity. So yes, this will have an acceleration. You cannot avoid it. F equals ma will tell you T plus mg is ma, and the a that you want in this problem, if it's moving in a circle, is mv squared over r. So it is accelerating. And the difference between this one accelerating, and let us say I go to the loop, and I drop an apple. Forget the track. It's got mg acting down. It's accelerating too. What's the difference between these two? Here you start with zero velocity. You accelerate downwards. That means you pick up a downward velocity, as a result of which you keep falling down and picking up more and more speed. The same acceleration is experienced by the cart also, and a little more because t is also pushing down. But there, the change in velocity over a tiny amount of time is not added to zero velocity, but to this large velocity it has at that instant. And the tiny increment in velocity, if added this way, will produce a velocity in that direction. And what that really means, if you wait a small amount of time, this thing is going along the new velocity direction. So that's the difference between, so the acceleration is the same for a falling apple as for the loop cart. But in the apple's case, it is added to zero initial velocity, so the acceleration and the velocity are the same, namely down. If you have a huge velocity to which you add a tiny change in velocity in the downward direction, you rotate the velocity vector. That just means that as it goes around the circle, the velocity vector is constantly tangent to the circle. There's another way in which people understand this. If you're on the earth and you are standing, say, on a building, and you fire a gun, it goes like that and it hits the ground because of acceleration due to gravity. If you fire it a little faster, it'll go there. There'll be a certain speed at which it keeps falling but doesn't get any closer to the center. That is, in fact, how you launch a bullet into orbit. So what's the first thing you should do when you fire this gun? move away because it's going to come back and get you from behind. Okay? All right, that's a very useful lesson. So you might think, hey, I shot it in that direction. It's not my problem. Like everything else, it'll come back and get you when you least expect it. But this is how you have. So is this thing falling or not? It is constantly falling. But the earth is falling under it, so it's endless search to come to the earth. Whereas if you drop the bullet, it'll just fall and it'll hit the ground. That's what we always think is drop. Okay, so this is something I did in a rush, and I didn't want that because this is really the part of physics which is not intuitive, and I think we all know what the main part is. The main point is velocity is a vector, and its value can change due to change in direction, not change in magnitude. Yes, sir?
That negative or that downward or change in velocity,
Right.
what is that equal to?
Okay. If you wait a certain time delta t, then the acceleration is v squared over r. Put the v, put the r, get some number, multiply by the delta t, 1/10 of a second. That will be the change in that time. So in that time also, the guy would have moved over in the circle a little bit, just precisely so that at that point, your new velocity vector is tangent to your new location. So this little delta v I drew is not a fixed number. It depends on how long I want to wait. Calculus says wait infinitesimal amount of time. In practice, wait 1 femtosecond and it'll be fine. Okay, today is very, very important concept I want to introduce. It's a very robust and powerful concept. It has to do with energy. It is powerful because after the laws of quantum mechanics were discovered in the subatomic world, we basically gave up on many cherished notions. You know, you must have heard that particles cannot have a definite position and definite velocity at a given time. They don't have any trajectories. You see a particle here now, then you see it there. That's true because they are observed events. What happens in between? You might think they have a trajectory, but they don't. Forces are not well defined because if you don't know where the guy is, you don't know what the velocity is, you don't know what the acceleration is. So most of the ideas of Newtonian mechanics are basically surrendered. But the notion of energy turns out to be very robust and survives all the quantum revolution. In fact, there was a period when people were studying nuclear reactions, and the energy you began with didn't seem to be the energy you ended up with. So something was missing. So Niels Bohr, father of the atom, said, maybe the law of conservation of energy is not valid. Then Pauli said, I think I put my money on the law of conservation of energy. I would postulate that there is some other tiny particle that you guys cannot see that's carrying away all the missing energy. That was a very radical thing to do in those days when people did not lightly postulate new particles. Nowadays, if you don't postulate a particle, you don't get your PhD in particle physics. Those days, it was very radical, and the particle was not seen for many, many years. It was called the neutrino. Nowadays, neutrinos are one of the most exciting things one could study. There's a lot of mysteries in the universe connected with neutrinos. Okay, so energy is a concept you're going to learn. Here's again a place where I ask you, don't memorize the formulas and start plugging them in. Try to follow the logic by which you are driven to this notion, because then it'll be less luggage for you to carry in your head. And I'll try to make the notion as natural as possible, rather than saying, this is my definition of energy, this is the definition of kinetic energy. Let's ask, where does all that come from? Now, how many people have seen kinetic and potential energies in your past? Okay, if you haven't seen it, that's fine. This is not something you're supposed to know. If you know it and you learned it properly, it'll be helpful. But you don't have to know that. You just have to know what we have done so far. So let's go back and ask a simple question. When a force acts on a body, what is its main effect? What does it do? Yes?
It changes its motion.
Be more precise by when you say changes its motion. What does it mean to change its motion? Yes?
It accelerates the object.
Right. That's from Newton's law. That means it changes the velocity. So let's, for a moment, in fact, for the entire lecture today, go back to one dimension. Then we will do the whole business in higher dimensions. In one dimension, changing the velocity simply means speeding up. So bodies are going to speed up and forces act on them. That we know. We're going to find a relation between how much speed is accumulated when a force acts on a body. We're going to derive that. So let us take an example where the force is in the x direction and it's some constant. Constant meaning it's not varying with time. Somebody decides to just apply 10 newtons constantly to a body. What does that do? That produces an acceleration, which is F over m, right? That's Newton's law. That's a constant acceleration. So let's go back to lecture number 1. Lecture number 1, we learned that if a body has constant acceleration, then the velocity at the end is the velocity squared in the beginning plus 2 times a times the distance traveled. This is what we learned long back. This is just kinematics. In those days, we didn't ask, why is it having a constant acceleration? You were just told. It's a constant acceleration, just go ahead. Now that we learned dynamics, we know acceleration has a cause, namely a certain force. So I'm going to write here, as you can imagine, F over m in the place of a. But I'm going to make one more cosmetic change in notation. In all these energy formulas, rather than calling the initial velocity or initial anything with a subscript 0 and the final is no subscript, we're going to use a notation where the final quantities are denoted with a subscript 2, initial quantities are denoted by a subscript 1. In other words, if initially the body had a velocity v1 and then it had an acceleration a for a distance d, then the relation between final and initial velocities is this. So let's put that F over m here and let's put a d. Since we are interested in the effect of the force, we want to see what the force did to the velocity. What you find here is that if you want to find the change in the velocity, of course you should take this guy to the left-hand side, right? Take it to the other side, and you want to isolate the force, so bring m over 2 to the left-hand side. So do that in your head, and what you get, m over 2 v2 square minus m over 2 v1 square is F times d. This is a very important concept. It says when the force acts on a body, it changes the velocity, and it depends on how far the force has been acting, how many meters you've been pushing the object. It's clear that if you didn't push it at all, then even though force is acting, velocity hasn't had time to change. So it seems to depend on how far the force acted. And the change is not simply in velocity, but in velocity squared. That's what comes out. Then you realize that it's the most natural thing in the world to give this combination a name, because that's what comes out of this. That combination is called the kinetic energy, and I'm going to call it K2, meaning K at the end minus K at the beginning is F times D. So F times D is denoted by the symbol W, and that's called the work done by F. That's how we introduce a notion of a force times distance as the definition of work. This is how people, you can say, why did anyone think of taking the combination F times D? Well, this is how it happens. So you need to have a unit for this, which is actually Newton meters, but we are tired of calling everything a Newton meter, so we're going to call it a joule. So joule or J is just a shorthand for Newton meters. All right, so let us now write down this following expression here. Delta K. Delta K in anything we do is a change in any quantity. It's called delta of that quantity. Delta K is a change in K is equal to the F times the distance traveled. Let the distance traveled be some tiny amount delta X. This formula is valid even if D is 1 kilometer, as long as force is constant. But I'm saying let's focus on a problem, whether the force is constant or not, over a tiny interval in which the body moves the distance delta X. Then we find that the change in the kinetic energy is force times delta X. Now, what if there are 36 forces acting on the body? Which one should I use? I'm pulling and you're pushing, and it's got to be the net force, because Newton's law connects the net force to the acceleration. If you and I have a tug of war and we cancel each other out to zero, then there's no acceleration. So, you got to go back to the definition. This is very, very important. This F better be the total force. I should really use a subscript T for total, but I don't want to do that. When we write F equals ma, it's understood F is everything. We will come back later to the notion of what happens if F is made up of two parts. So maybe I'll just give you a simple example. Here's a body, right? And I'm pushing it this way, and you're pushing it that way, let's say with equal force. And the body could be at rest, or if the body had an initial velocity, it'll maintain the initial velocity, because velocity is for free. Then you can ask, what does this theorem say? This is called the work energy theorem. The work energy theorem says the change in energy is equal to the work done by all the forces. In this case, there is no change in energy, but there are two forces at work that cancel. Then it turns out that it's sensible to define the work done by me, which is equal to F times the distance it traveled, and the work done by you will be in fact given a minus sign. So when do we attach a plus sign and when do we attach a minus sign? If you go back to the whole derivation, it was understood that A was a positive quantity. Then everything works. But if the body is moving to the right and I'm pushing to the right, then the work done by me is positive. And if you are pushing to the left and the body still moved to the right, the work done by you is negative. In other words, if you get your way, namely things move the way you're pushing, the work done by you is positive. If people are pushing you counter to your will, in the opposite direction to your force, work done by you is negative. So here's a simple example. I have a piece of chalk, and I'm lifting it at constant velocity from the ground. Its kinetic energy is not changing. That means the total work done on it is zero, but it's not because there are no forces on it. That is gravity acting down, that is me countering gravity with exactly the right amount. I'm applying a force mg. So work done by me would be positive because I want it to go up, and it goes up. So if it goes up by an amount h, work done by me is mg times h. Work done by gravity, in the meantime, is minus mg times h. So the total work done is zero. So this formula says this is the total force, but I'm telling you, if you take that work done and call it delta W, it may be a result of many works. Work done by me, work done by you, work done by somebody else. Some are positive, some are negative. You add them all up. So that is the notion of work done by one of many forces acting on a body. And the total work done is the algebraic sum of the work done by all the forces. All right, so we got this result. Let's do the following. Let us imagine all this occurs in a time delta t. Then delta k over delta t, which will eventually become dk dt, if you take all the proper limits, becomes f times dx dt, which is force times velocity, and that's called power. So power is the rate at which work is done. For example, if I climb a 12-story building, I've done some work. My m times the g times the height of the building. Now I can climb the building in 1 minute, I can climb the building in 1 hour, the work done is the same, but the power is a measure of how rapidly work is done. That's why it's the product of force and velocity. So the units for power are joules per second. Now that also has a new name, which is watts, or just W. You may use a kilowatt, which is kW, little k times W is 1,000 watts. So if you've got a 60-watt bulb, it's consuming energy at the rate of 60 joules per second. That's the meaning of a 60-watt bulb. Okay, now I'm going to do the next generalization, which is when the force is not a constant, but varies with x. So do we know any example of a force that varies with location?
Spring.
Spring is one example. Even gravity, I think we know it's not a secret. The force of gravity is mg near the Earth, but if you go sufficiently far, you will notice gravity itself is getting weaker. It'll still look like mg, but g won't be 9.8. G will become 9.6 and 9.2 and 9.1 will decrease. But the variation of gravity in terrestrial experiments is pretty small, so we won't worry about it. But the force of a spring definitely varies with x in a noticeable way. And the force of a spring, so one concrete example is what you all seem to recognize, is this one. So then we have to ask, what is the work energy theorem when the force is itself varying? So let's draw ourselves a force which is varying. So here is x, here is my force, it does something. F equals kx or minus kx is a particular graph. I'm just taking any function of f that I want. Now the acceleration is not constant because the force is not a constant. So if you wait for 1 hour, the change in kinetic energy is not simply force times distance, because what force are you going to use? It was something now, it is something later, it's positive now, it's negative later. So we cannot apply this formula because f is not a constant. So the usual trick in calculus is find me an interval in x which is so narrow, and I'll make it as narrow as you insist, so that during that period I'll think that f is a constant, and the constant value of f is just the function f at that time x, at that time where the location is x. So for that tiny interval, I can still say that f is constant, f over m is some constant over the tiny interval. Then the change in kinetic energy will be then f of x times delta x. Then you wait a little longer. You go to a new place. Then you got a new value of the force, maybe somewhere here. Then that times delta x is the work done in that region. But geometrically, fx times delta x is the area of the little rectangle whose base is delta x and whose height is the function f at that time. So if you eventually went from here to here, let me call that point as x1, and let me call the ending point as x2, then the work done by you is really given by the area under that graph. And in every segment, you pick up the change in kinetic energy, you add it all up. When we say add it all up on the left-hand side, all the k's will add up to give me the final minus the initial kinetic energy. This one is what is written in the notation of calculus as fx dx from x1 to x2. Now, this is called the integral of the function f of x. Now again, in a course at this level, I'm assuming that you guys know what an integral is. Even if you never heard of an integral, if I give you a function and you never heard of calculus, you can still deal with this problem. Because you'll come to me and say, give me your function. I'm going to plot it in some kind of graph paper with a grid on it. And I'm just going to count the number of tiny squares enclosed here. That's the area, and that's the change in kinetic energy. So integration is finding the area under graphs bounded by the function on the top, x-axis below, and two vertical lines at the starting and ending points. Now a little digression. Even though you're supposed to know this, I want to make sure, part of my No Child Left Behind program, that you all follow this. So if you never heard calculus or integral calculus, this is going to be a 2-minute, 3-minute introduction. There is a great secret, which is that if you give me a function and you tell me to find the area under this from x1 to x2, I can go to the graph paper and draw that, or there is quite often a trick. You don't have to draw anything. You know, and I will tell you a little more about what it is. If you give me a function f of x, the area under this graph happens to be the following. There is another function g of x to be specified in a moment, and you just have to find g at the upper limit minus g at the lower limit, and that will be the area. And who is this mystery function g? It is any function whose derivative is the given function f. So the whole business of finding area, which is solved around Newton's time, is if you have a function, you want the area under it, you go and think of a function whose derivative is the given function. So this is the opposite of taking derivatives. Differentiation is an algorithmic process. You take f of x, you add a delta x to the x, you find the change in f, divide by delta x. Given any function, you can do that. This is the opposite. This is guessing the function g whose derivative is f. So if I say f of x equal to x cubed, then g of x is that function whose derivative is x cubed. So I know I got to start with x to the fourth, because when I take derivatives, it will become an x cubed, but with a 4 in it. So I fight that by putting a 4 downstairs, and that's the function g. Yes?
Shouldn't there be a C?
Yes, that is the plus c, where c is, of course, velocity of light. Okay. Now, why is this plus c there? She's quite right. Because if you got a function whose derivative is something, adding a constant doesn't change the derivative. Then you can say, well, we are in trouble now because you told me to find the function g, and you're telling me the world cannot agree on what g is because I've got one g, you got another one with different constants. But the beauty is that when you take this difference, I may not put the constant and you may put the constant, but it's going to cancel out. So most of the time, people don't bother with the constant. Sometimes it's very important to keep the constant. It plays a special role, but we don't want that here. We'll just call this the integral. So maybe it's again worth asking for a second, why is this true? Why is g the function whose derivative is f? Why is that the answer to the problem? Well, one way to think about it, this is really more for your completeness than anything else. Suppose there is a function f, and I'm finding the area. Let me find it up to the point that I'm going to call x2. For the starting point, let me just pick 0. This is the area I'm looking for. And I write it as f of x dx from 0 to the point x2. You agree that as I slide x2 back and forth, the area is varying with x2, so it's legitimate to call that a function of x2. Function is anything that depends on something else, and we all agree that if the point x2 moves, the area moves. This is my shorthand for the area. The starting point is nailed at 0. This is g of x2. Then let's ask, what is g of x2 plus delta? That is the area till this point. That we denote as f of x dx from 0 to x2 plus delta. That is g of x2 plus delta. So what is the difference between the two? Difference between the two is g of x2 plus delta minus g of x2. If you look at the graph, the extra area that I have is this thing. And that is clearly equal to f at the point x2 times delta x. In other words, by how much is the area changing when I change the upper limit? Well, it's changing by the height of the function at the very last moment times the change in x. Well, we know what to do now. Divide by delta x and take the limit, and you can see that f of x2 is dg dx at the point x2, but the point x2 is whatever point you want, so we drop the label and we just say that f as a function of x is dg dx. This is the origin of the result, that the area can be found if you can find the inverse derivative of the function. So let's keep a couple of popular examples in mind. One, if f of x equal to constant, then g of x is equal to constant times x. If f of x equal to x, then g of x is equal to x squared over 2. As you know, the integral of x to the n is x to the n plus 1 over n plus 1. There are integrals for all kinds of functions. And you check them by taking derivatives and make sure you get back your f. All right, suppose this is what we learned from the math guys. Then go back to the work energy theorem and see what it says. K2 minus K1. Oh, by the way, I didn't complete one story. Let me finish that. This was, if g of x2 was the area from 0 to the point x2. G of x1 is the area from 0 to the point x1. Then it's perhaps clear to you that if I only want the area between the point x1 and the point x2, I can take the area all the way up to x2, subtract from it the area all the way up to x1. And that's, of course, the claim that this integral f of x dx from x1 to x2 is g of x2 minus g of x1. That's the reason the integral is given by a difference of this g. So let me use a shorthand notation and call g of x2 as simply g2. G of x1 is g1. You should understand, g2 means g evaluated at the final point, g1 is g evaluated at the initial point. So you have got k2 minus k1 is g2 minus g1. But g is some definite function of x. You got to understand that. For example, it could be x2 square over 2 minus x1 square over 2 in the problem where f is equal to x. Then let's rearrange this thing to read k2 minus g2 is equal to k1 minus g1. So the work energy theorem says that if a force is acting on a body, a variable force, associated with the force is the function g, a variable function of x, whose derivative is the given force. Then at the beginning, if you take the difference of kinetic energy minus the value of g2, it'll be the same, I'm sorry, k1 minus g1, it'll be the same as k2 minus g2. Now we don't like the form in which this is written. We have to make a little cosmetic change, and the cosmetic change is to introduce a function u of x, which is minus this function g of x. So once you do that, you got to remember now the force is equal to minus the derivative of this function because of the minus sign relating g to u. Then we can write it as k2 plus u2 is k1 plus u1. And that combination, if you call that as E2, and you call this combination as E1, we are saying E1 equals E2, and that's called the conservation of energy. So what does conservation mean? Conservation of energy in physics has a totally different meaning from conservation of energy in daily life. Here it means when a body is moving under the effect of this force f of x, you agree it's gaining speed or losing speed or doing all kinds of things. So as it moves around, it's speeding up and slowing down. So its speed is definitely a variable. But a certain magic combination connected to the velocity of the object and to its location, u depends on x, that does not change with time. And it's very useful to know that does not change with time, because if you knew the value of e, E1 equal to E2 equal to some fixed number e at one time, you know e at all other times. So let's take a simple example. So we take a rock and we drop it. We know it's picking up speed. We know it's losing height. So you may think maybe there is some combination of height and speed which does not change in this exchange. And we find the combination by this rule now. In the case of gravity, F is equal to minus mg. Therefore, u is equal to mg times y. Because minus du dy will now be my F. Then we may conclude that 1/2 mv squared plus mgy at the initial time will be equal to 1/2 mv2 squared plus mgy2 at the final time. And that is and the whole thing can be evaluated any time. You take any random time you want. The sum of these two numbers doesn't change. And that's a very, very powerful result. So I'm going to give you one more example later when you can see the power of this. But in the case of gravity, this is what it means. So this agrees with their intuitive notion that when you lose height, you gain speed. When you lower your y, you gain speed. But it's much more precise than that. Instead of saying vaguely you lose and gain, 1/2 mv squared is the part connected with the speed, and mgy is the part connected with the height, and that sum does not change with time. So let's go back to the mass and spring system. In the case of mass and spring system, if you have a mass connected to a spring, then we say here 1/2 mv square plus 1/2 kx square equal to E is a constant. That means find it at any initial time 1, find it at any final time 2, add these two numbers, the total will not change. So let me put that to work. Let me use that in a calculation. So I say, here's a spring, here is where it likes to be. I'm going to pull it to a new location, A. X equal to 0 is where the spring likes to be. I'm going to pull it by an amount A, and I'm going to let it go. And I want to know how fast the guy is moving when it comes back to, say, x equal to 0. If you go back to Newton's laws, it's a pretty complicated problem. You've got to think about why it's a complicated problem. Because you start with a mass at rest. If you pull it by an amount A, a force acting on it will be minus k times A. That'll produce will produce an acceleration, right, Ka over m, which will give it a new velocity by the time it comes here. But once it comes to the new location, a little later, a different force is acting on it because the x is now different. So the acceleration during this interval is different, and the gain in velocity in that interval will be different from that in the first interval. You got to add all these changes to find the velocity here. That's a difficult proposition. But with the law of conservation of energy, you do that in 1 second. In fact, let's do it not just to be at the midpoint here, but at any point x measured from equilibrium. Because we will say initially 1/2 mv1 square plus 1/2 kx1 square is equal to 1/2 m v2 square plus 1/2 k x2 square. This is the truth. This is a constant, does not change with time. Now, to get some mileage out of this, you got to know what the constant value is. Well, we know what it is in the beginning, because when we pulled this guy, at that instant, we knew it had no velocity, and we knew it was sitting at the point A. So we know 1/2 ka square, that is the total energy of this mass and spring system. That's not going to change with time. We like to say that at the initial time, all the energy is potential energy, there is no kinetic energy, because there is no motion. At any subsequent time, this number has to be equal to what you get. Let me drop the subscript 2 there, let it stand for some generic instant in the future. This much we know. Now, do you see that we can solve for the velocity at any location x? You pick the x. If you want x to be 0, that's very easy. You kill that term, you balance these two, you cancel the half, and you can see that's a formula for v squared. V squared is going to be ka squared over m. That is going to be the velocity when it swings by this midpoint. But you can pick any x you like. If the x was not 0, but 0.1, well, put the 0.1, take it to the other side, and solve for v. So this is one example of the law of conservation of energy. So the power of the law of conservation of energy is if you knew the initial energy, you don't have to go through Newton's laws. And you will find in all the problem sets and many exams, when a problem is given to you and you're told find the velocity of something, you should try whenever possible to use the law of conservation of energy rather than going to Newton's laws. So if you want to know what have we done, how come finding the velocity seems so difficult when I described it to you earlier and we have done it? The answer is, if you tell me the force of the spring is a function of x, I have done that integral in the work energy theorem once and for all. The integral of the spring force has been integrated once and for all, and that's what the potential energy is doing. Potential energy comes from integrating that force. All right, so now let's take another problem where there are two forces acting. Yes?
Could you just explain really quick how you got the 1/2 in front of the kx squared for the energy?
Let me see. Here?
Down at the bottom of the center, yeah.
Here?
Is it just because of the integration?
Yeah, for a spring, I think we said here, if the force is x, the potential energy is G is equal to x squared over 2, U will be minus x squared over 2. So if the force is minus kx, then you have to find a U so that minus du dx is equal to minus kx. And the answer to that is U is kx squared over 2. So if you knew the force, you just find the function U by asking whose derivative gives me F with a minus sign, then you are done. That's the potential energy for that problem. Now let's take another problem. A mass is hanging from the ceiling. Then it's got two kinds of potential energy. One is just a gravitational potential energy, and other is the spring potential energy. And that's going to come because K2 minus K1 will be the integral of f of x dx. I'm sorry, let's call it dy, f of y dy from y1 to y2. And this f of y will have two parts. The force of gravity, I'm tired of writing the limits, then the force of the spring from 1 to 2, from 1 to 2. Right? There are two forces acting on it. This one will be mg y2 minus mg y1. This one will be 1/2 k y2 squared minus 1/2 k y1 squared. So every force acting on the body will turn into a potential energy because the force, Newton's law says, work energy theorem applies to the total force. The total force is two parts, and you can do two integrals. Each integral is an upper limit minus lower limit of some function, and this is what you get. Oh, I think I made one mistake here. I think this should give me, yes. This is, overall sign is wrong in these equations. Really, there's a minus in that and minus in that. In other words, the work done by the force, if there's only one force acting, is really U1 minus U2. You see why I got the sign wrong? When you do the integral in calculus, integral of f is g2 minus g1, but g and u are minuses of each other. So integral of force will give you u initially minus u finally, so it should really be plus mgy1 minus mgy2. So the law of conservation of energy for this object will be that 1/2 mv squared plus mgy plus 1/2 ky squared is the total energy and will not change. So this mass can bump up and down and go back and forth. If you knew the total of these three numbers at one instant, you know the value at any other instant. For example, if you pulled it from its equilibrium by 0.2 centimeters and you released it, and you say, what's the speed when it's 0.1 centimeters away? It's very easy because you know the initial energy was all spring energy and gravitational energy. At any later time, if you knew the y, if you knew the position, you know the potential energy. That's the whole point. Potential energy depends on where you are. Kinetic energy depends on how fast you're moving. And some combination of where you are and how fast you're moving is invariant, does not change with time. So if you tell me where you are, I will tell you how fast you're moving. By the way, remember the kinetic energy enters as v squared. You can imagine when you solve for v, you're always going to get two answers. Why is that? Does it make any sense? Yes?
Because you're going to have the same potential energy, like in that spring problem if you're oscillating. Like when you're in a certain position, you could be either moving down or up, but you're still
Right.
going to
Or if a spring is going back and forth, at a given point x, you can have two velocities because you could be going away from the center or you can be going back towards the center. So this tells you the velocity on those two will be related by a minus sign. Right? If you pull the spring this way, when you go through the origin, you say, what's my velocity? I'll get two answers because I could be going to the origin or I could go the other way and on the way back again past the origin. So at every x, you'll get two velocities. And that agrees well with the fact that v squared is what you will solve for, and because it's quadratic, you will get two answers, and you should get two answers. You should be expecting that. Okay, now we are going to find one bad boy, bad girl, bad person, which is going to ruin this whole thing. That is, you know what I'm talking about here? Yes?
Friction or not considered?
So friction is a force acting on a body. So what's the thing I should try to do? Let's take a body with only friction acting on it. Let's not worry about anything else. Or maybe friction and a spring. So I try as usual to get a law of conservation of energy when friction is acting. And you will see that I will not succeed. And it looks like everything here is watertight, right? Everything looks good. You tell me the force acting on a body. I integrate the force from start to finish, and I call that the difference of potential energies. Then I've got my result. Try to follow this logic. K2 minus K1 is the integral of the force. Integral is gx2 minus gx1, or which is ux1 minus ux2. You can rearrange it to get K2 plus U2 is K1 plus U1. Looks like you can always get law of conservation of energy. And we want to know why that fails when there is friction. Okay. Why does it fail when there is friction? So when there is friction, let me try to do it again. K2 minus K1 is the force due to the spring, which is whatever minus Kx. Let me do that integral, plus the force of friction dx from x1 to x2. This one is from x1 to x2. And we saw what this is. Let me write it one more time. 1/2 k x1 squared minus 1/2 k x2 squared. If you didn't have friction, you are done. Because you can get kinetic plus potential for spring is kinetic plus potential. Why don't we just integrate the force of friction and then turn that into a u, and then we're done. What's going to be the problem? Let me just give some, anybody else want? Yes?
It's always against the direction of motion, so it would be always, would be changing the direction of force.
Okay.
Certain intervals.
What was your,
You can associate a potential function with friction because it depends on the path, not only the initial position and the final position. The antiderivative only considers the final and the initial position.
right, but let's suppose I'm somewhere and I'm pulling a block and there is some friction, that is a force F. At the location, that's my F. Why don't I just use the value of F? Yes?
Energy is lost due to heat.
Pardon me?
Energy is lost due to heat.
I know, but see, you are saying something else which is peeking ahead into the book. But right now, what's the problem with integrating the force of friction? Yes?
I was just going to say the energy for the force of friction is no longer within the system.
No, but you're all telling me why there is a loss of mechanical energy, but I'm just a mathematician. I'm saying, give me a force, find its integral. What's the problem? Yes?
Is it because the function for the force of friction depends on the velocity?
Yes. I think somebody else said that earlier also. The force of friction is not a function of x. You might say, what do you mean? I'm pushing this guy. I know how hard it's pushing me back, but I'm telling you, now push it the opposite way. Then you'll find the force of friction at the very same location is pointing in a different direction. Whereas the force of a spring is the force of the spring. It's minus kx whether you're going towards the spring or you're going away from the spring. Try to think about that. Same with gravity. Gravity is pulling you down with a force minus mg, and it doesn't care whether the chalk is going up or coming down. On the way up, it's pulling it down. On the way down, it's also pulling it down. Because at a given location, there is a fixed force. So the problem is not the force varies with x or y, but the force is a function only of x. But if it's a function of x and velocity, then you also have to know the velocity, and no one's giving you then a definite value for the velocity, because in the vibrating mass and spring, velocity can have either sign. Therefore, we do this integral, but we don't do this. Even though I write it this way, mathematically it's wrong, because the force of friction, is it really a function of x? I will tell you in what limited sense it is a function and what technical sense it is not. Let's defer that for now. Take all these guys to the left-hand side. So this is K2. This will become U2. So you will get K2 plus U2 minus K1 plus U1 is equal to this last thing, work done by friction dx from x1 to x2. And the question is, can I do the integral? The answer is, if you just tell me x1 and x2, then that's the point you're making. I cannot just do an integral, because I will have to know the whole story. But in limited cases, I can do this. Suppose I pull the mass by an amount A, and I let it go. But now there is friction. I think we all know that if it came to the center, it won't be going quite as fast. We also know when it overshoots the other side, it will not go back to minus a. Normally, it will go back to minus a. Everyone knows why it goes back to minus a, right? When you go to the other extremity without friction, your energy is all potential. If it was 1/2 ka squared to begin with, it's got to be 1/2 ka squared at the end, except a can become minus a without changing the answer. That's why it'll go from a to minus a. But when you got friction, I cannot say the energies are equal because I got to do this integral. For this part of the journey, from here to here, during that part of the journey, the force is a well-defined function. Namely, it is a constant value minus mu times mg, and it is acting this way. So for this part of the trip, I can do the integral. It's very easy to find out what it is. It's minus mg times mu kinetic times the distance traveled. Of course, it's a little more complicated now. You have to tell me where you want your velocities. You might say, find the velocity at x equal to 0. If you want me to do that, the distances traveled is the original displacement. That's what is the stuff on that side. And here, K2 is 1/2 mv squared, which is what I'm trying to find. I am at the origin, so it's 1/2 k times 0 squared. No potential energy. Initially, there was no kinetic energy, but there was potential energy, 1/2 ka squared. You follow that logic now? This is the difference in energies due to the conserved forces, the conserved energies, but their difference E2 minus E1 is no longer 0, but it's given by this number. So I can calculate it for this part. I can even ask, this is one of the homework problems, I think, you're asked, how far does it go to the left? Well, what do? Let's call the place where it goes to the leftmost extremity, as A prime. Then we don't know. So there, when you go to K2 plus U2 minus K1 plus U1, you will go back to this formula. First of all, the distance that the force of friction acts on is how much? It's the distance A to come here and another A prime to go to the left. A prime is a magnitude of how far you go to the left. And likewise, on the left-hand side, you got to have the total kinetic plus potential minus kinetic plus potential. At the end of the day, you only have potential energy, 1/2 k A prime square, no kinetic. And initially, again, you only had potential energy, 1/2 k A square. You will see that A prime now satisfies a quadratic equation. You can solve it. But what is the point? The point is you cannot do this integral once and for all and say the answer depends on the endpoints. In this particular problem, if you told me you're doing this part of the journey, during that part of the journey, because for the entire trip, the velocity had a particular sign, namely to the left, force of friction had a definite magnitude and sign, namely to the right, and then of course it's as good as any legitimate function, and you can do the integral. In fact, the force is a constant. You can pull it out of the integral, and the integral dx is just the distance traveled. Okay? So work done by friction, it will always come out negative. And you should keep track of that. Okay, so the final bottom line for law of conservation of energy that you guys should remember is the following. You take all the forces acting on a body. So let's do it one more time in our head so you know where everything comes from. Everything comes from this result. K2 minus K1, which is the work done, is the integral of all the forces. Divide the forces into forces that depend on location only and not on anything else, like velocity. Let me just divide them into two forces. One is a good force, dx, and one is a force of friction, dx. This guy will turn into potential energy difference. Let me just take one good force and the force of friction. If you had two, each will generate its own potential when you do the integral. Then we may then say E2 minus E1, that's the same as K2 plus U2 minus K1 plus U1 is equal to the work done by friction. Work done by friction is the shorthand for that integral, which you can do only, you must divide the motion involved into pieces. For example, if you have a mass that swung to the left, then turns around and goes back to the right, of course, again, it won't come back to the original A, it'll come to a smaller number. That's because there's more loss of energy on the return trip. For the return trip, you must do the problem separately. On the return trip, you start from this A prime that you found, then start moving to the right. Now friction will act to the left. So you must divide the motion into segments. During each segment, the force should have a definite direction and magnitude, so you can do the integral. The point is there is no universal formula for f of x due to friction. So in one dimension, that's all it is. Between the good and bad forces, those which lead to potential, those which don't, the difference is the good forces are functions of x, bad forces are functions of x and something else, so that at a given x, it's possible to have two values for that function. Mathematically, we don't call it a function. That's why you cannot do the integral once and for all. So this is the law of conservation of energy. Okay? All right. Now, what I have to do here for the remaining time is a little more of some mathematical preparation for what I'm going to do next. What I'm going to do next is to go to higher dimensions, and we got to make sure we all know some of the mathematical ideas connected with higher dimensions. So I'm going to start off with some things, and this is like a mathematical interlude. Again, I told you if you're not strong on some of these things, you should read this math book I mentioned to you on basic training. It'll certainly cover these topics, but you don't have to have that. I'm going to tell you now how to do it. So the math idea that I'm going to use, so this is really a mathematical digression to make sure everybody knows. They're very simple things, but we do it all the time in physics, so I want to make sure you guys can also do that. So let's take some function, f of x, that looks like this. This is f of x. This is x. And let's say you start here at some point x, and I'm going to go to a nearby point x plus delta x. Delta x is exaggerated so you can see it. So it's actually, in the end, going to be a very small number. The question is, what is the change in the function in going from here to here? So we all know what it is. That is the change in the function. We are going to need approximations to the change in the function. A useful approximation is to say, let's pretend the function is a straight line and keeps going with the slope it had to begin with. You can see that if the function is not curving up or down too much, you almost got the right change in f. And what is that change in f? That change in f is the derivative of the function at the point x times the change in x. But it is not an equality. It's not an equality because there is this little guy on the top that you have missed. Because the function is not following the same slope that you had to begin with, it's curving up. So let's take a concrete example. Suppose f of x is equal to x squared. Then f of x plus delta x is x squared plus 2x delta x plus delta x squared. Therefore, the change in f, you got to take it to the other side. Change in f is 2x delta x plus delta x squared. 2x delta x, 2x is, of course, what you realize is the derivative of the function at that point. And that's giving you this part, but there's a tiny portion on the top, which is delta x squared, that you're not getting. If the function was x cubed or x to the fourth or hyperbolic cosh of x, there'll be more errors. But the point is the change in the function has a leading piece that's proportional to delta x, then there are corrections that we say mathematically are of higher order in delta x. So if delta x is made very small but not 0, then it's a very useful formula to know that the change in function in going from one point to another point is this rate of change times the change. I don't think anything could be more natural than that. But we should be comfortable by saying, it's naively people say, well, you should do that because in calculus you're canceling this delta x with that dx. That's not what we're really doing. We all know that this stands for a certain limit, but the limit stands literally for the slope which is at that point. So if functions had only one slope and they never changed their slope, and you knew that slope, then if you know the value to begin with, you can find the value a mile away from where you are because it's going at the same clip. But most functions, of course, will change their slope. And for that reason, there will be an error in the formula you get if you use this. But if delta x is very, very small, and it's your intention in the end to make very, very tiny delta x's, then we say we will use this approximation. That's very simple, but it's very useful to know. So let's take an example of this function, of this rule, because I'm going to use it all the time. So one example is f of x is equal to 1 plus x to the n. Well, f of 1 is just 1. Suppose you go to a nearby point which is x away from the point 1. So this x is really like your delta x. Then the change of the function will be df dx at the point 1 times the change in x. Yes?
Is it f of 1 equals 1 or f of 1 equals 2?
I'm sorry. Okay, that's right. F of 0, if you like. If x is equal to 0, the function has a value of 1. Then if you go to a neighboring point, so here's what I'm saying. The function does something, its value here is 1, and I want to go to a nearby point, which I'm calling x. Then df dx, you know, is n times 1 plus x to the n minus 1 times x. But you have to evaluate it at x equal to 0. So this goes away. Then you get nx. So the change in the function, this function, as you move off x equal to 0 is nx. So what we are saying then is 1 plus x raised to the n is 1 plus nx plus tiny numbers if x is small. That is a very useful result. If something looks like 1 plus x raised to a power, and if you're not going too far from the point 1, namely if your x is very small, then don't bother with doing the whole 1 plus x times 1 plus x n times. It's approximately equal to 1 plus nx. So let me give you one example. You will use this later on. According to relativity, a mass of a particle is given by this. If the body is sitting still, it has a certain mass. In Newtonian mechanics, we say the mass is the mass, and that's the end of it. In relativity, you don't have to know the origin of this. That will be taught to you in due course. But it just says particles with velocity have a mass different from when they are at rest. And this is the velocity, and c is the velocity of light. This is the exact formula. Now, most of the time, we don't care about it because v over c may be 10 to the minus 10. And the square of that is 10 to the minus 20, and 1 minus such a number is negligible, and we just put it as 1. Suppose you want an answer that's good to some accuracy. I will write this as follows. It's m0 times 1 minus v squared over c squared to the power minus 1/2. You agree? That's what a square root in the bottom is. It's this power upstairs. Now we can write it as follows. m0. This is 1 plus x to the n. Okay? So the x that we use is minus v squared over c squared, and the n that we use is minus 1/2. That's what I'm using in this formula. X is minus v squared over c squared, and n which is the power to which I'm raising, is minus half. Therefore, this is equal to 1 plus v square over 2c square, plus corrections which are negligible if v square over c square is very small. This is a very useful result. It tells you the mass variation is that it's the mass at rest plus m0 v square over 2c square. It's a very useful formula. Sometimes this formula is much more friendly to use than the exact formula. You cannot beat the exact formula. It's the exact truth. But if you're interested in that exact function for small values of v over c, it's much more useful to use this approximation. And you will have a lot of problems like this in your homework, now, later, everywhere else. So if I'm going to use it all the time, I should tell you what it is. So let me summarize what I've told you so far. First result is, if a function is known at a certain point, and you want to know its value at a nearby point, what are you supposed to do? That's not so hard to guess, right? For example, your tuition costs are so much this year at Yale. And we know how much it's going up every year. You can make a guess on what it'll be a year from now. Of course, in reality, it'll be higher than that because there are these other terms. But that's the best guess you would make. That's how we predict the future, by looking at past rates of change. That's very normal. The point is that you can predict the tuition a year from now maybe, but maybe not 5 years from now or 10 years from now, because there's inflation on top of inflation. That's like saying the rate of change itself has a rate of change. The slope here is not the same as the slope there. That's what the higher derivatives of the function do for you. So I will conclude by telling you one last result, which I'm not going to prove in this course, and you guys should learn from the math department, the following result. There is some crazy function, okay? This is f of x. I want to know what it is at the point x. I know what it is at the origin. If I know nothing else, how do I predict the future value of x, meaning for other x? I don't know. My best guess is, well, this is the number I knew, that's what it's going to do. But if I knew its rate of change here, its slope here, the next guess is it's the derivative of f at the origin times x. That's just what I did earlier. Instead of delta x, I'm calling it x. If x is small enough, it will work. But of course, x need not be small. If it gets bigger, it turns out you can do a little better by adding this. This is the second derivative of the function at the origin times x squared. And you can go on adding more and more terms. I'll just add one more term, which is 3 factorial times d cubed x, f over dx cubed times x cubed. This goes on forever. And it says that if you knew every derivative of the function at the origin, you can reconstruct the function. Not just infinitesimally close to it, but as far as you want to go. There are some mathematical restrictions on this, because there are infinite number of terms in this thing. When you add them all up, you may get infinity, which would be nonsense. So you should really sum up this infinite number of terms if they add up to a finite number. And if they do, that will give you the function here. What we have done is to just use the first two terms as an approximation. But what I'm telling you is there is something called the Taylor expansion of a function that allows you to know the function even here, macroscopically far from here, if you knew all the derivatives, and if you put those derivatives here, and if the sum added up to something finite, that finite thing is the value of the function at the new point. Here's an example you guys can take. F of x equals e to the x. Why don't you go home and work out the series for f of x at all points? You've got to remember that e to the x has the beauty that its derivative is e to the x itself, and its value at the origin of every derivative is simply 1, so this just becomes 1 plus x squared over 2 factorial, and that is in fact the expression for e to the x. And it turns out that no matter how big x is, this sum in fact adds up to a finite number that we call e to the x. In particular, what is e itself? E itself is e to the 1. E is e to the 1, so put x equal to 1, you get 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial. You do all that, you get 2 point something something, right? That's e. So this is a very powerful notion. If you knew all the derivatives of a function you can predict its value not only in the tiny neighborhood, but over a big distance. If you knew the first derivative and you were not very ambitious, look, logic is very simple. If x is a tiny number, x squared is even tinier, x cubed is even tinier. We got no respect for these terms. We just drop them and we stop here. Okay, I'll have something more to say about this later on, but for now, these ideas will be useful for what we're doing next time.